Thank you very much for joining us on this talk on deep learning with Neo4j. As you may recognize, I'm not Tom Benedictus, as is announced on the program. My name is Line Sørensen. I'm COO at Trifork. Tom was beamed up to a client, so today I will just do a very short introduction on who is Trifork, in case you don't know us, and then I'll leave the stage to Phil, who's going to take you through the conversation on deep learning with Neo4j. So who is Trifork? We run conferences. That's probably why some of you know us. I don't know if you know QCon conferences or go to conferences, then you may know Trifork. We do a lot of other things than that. We do implementation projects on some of the newer technologies, so Neo4j, which we are here to talk about today, Elasticsearch, React, Docker Mesas. We do mobile applications, and we're very active in the financial space as well. So we are here today, if you have passed by our table, we have a small brochure and a product sheet on fraud prevention, which is a product that we offer as well, based on Neo4j. We have 400 employees, and we have more than 6,000 attendees at our conferences every year. So we do a lot of the things that you experience today with Graph Connect. So this, you may know us from that. So what else do we do besides the conferences? In the space of NoSQL and search solutions, we work quite a lot with Neo4j, React, Elasticsearch. We do deployment management solutions, Docker and Mesas. And we also do a lot of customized mobile applications within the space of mobile banking, mobile payments, and so on. And then we have a whole academy branch where we do trainings, among others, in Neo4j and Elasticsearch. I won't say so much more about that. I'll rather leave the stage to Phil, but just mention one quick thing before we get started on the talk. We have a conference coming up in London in September called Go to London, and we are making a small draw today of 2 free tickets for this conference. So please pass by our small little booth, our table, and register your contact information with us. We will announce the winners tomorrow morning, so we can have everyone also that attends the reception here later today. So, thank you very much. I'll just leave the floor to Phil. Thanks.
Okay, thank you, Lee. Okay, so my name's Phil Winder. I'm an engineer at Trifork Leeds. I'm going to be talking today mainly about deep learning. This is actually part of a longer presentation which introduces Neo4j as well, but I thought I'd better skip that because that's already been done. So what the aim is, the overall goal, is to try and give you some inspiration to using some machine learning techniques, basically. It's a really interesting field, and I'm hoping that you'll go away with a bit of excitement and a bit of enthusiasm to go and look at it a bit more. So I'm going to start off by talking about deep learning. So what is deep learning? It is essentially an extension of machine learning. Machine learning is a field which attempts to do things in a way that a human would be able to do as well. So it started off with quite simple automated tasks at the dawn of computing, and has gradually got more and more advanced over time. The ultimate goal really is to be able to replace a human, act like a human, and make as good as, or if not better, decisions than a human can. So essentially, deep learning is an extension of this, and is just a grouping of a couple of those techniques within machine learning. So nothing fancy. But what's new today? Well, the advent of some of these techniques that I'm going to be talking about, they were around in the 80s. I've spoke to a few people today that said, wow, I came across that when I was X. Basically, the way in which we use them has improved. So back in the day, I'm going to be talking quite a bit about neural networks. And the whole idea about neural networks is that they were built to try and emulate and mimic the human brain, or the way that, on a very simple level, the human brain works. Back in the 80s, it was available, but it didn't work too well because the ways in which people tried to use it just weren't really fit for the job. So we've got new techniques, new training methods, and really the key new thing that's bringing it out into the public domain is the beginnings of the automation of feature engineering. So one of the bottlenecks in the past was that in order to use machine learning algorithms, you need features. And these features come from your data, but they're not raw data. They're something, they're numbers or metrics that describe your data in a decent way. In the past, you need a data scientist in order to do that. Now, these techniques are starting to bring this technology to a wider audience by removing some of those bottlenecks. So why? Why now? Why again? It always just comes down to data volumes. Lots of other people have mentioned it. The amount of data that we have to handle, even just on a daily basis in our normal lives, is growing massively and is becoming difficult to work with. So if we can get machines to do that, then it frees up our mind to do more interesting things like look at cat pictures or something like that. One of the key things from a business perspective, was that we can kind of remove some of the bias that people were introducing by doing their work. So computers are, unless they're programmed in such a way, they're not evil things. They will go about their job without any bias. You know, a human being makes mistakes. So we've already seen many examples of where machines make less mistakes than humans. Mitigates risks, improves data security. I'm going to skip them because I've got lots of slides I want to get through. So what is deep learning? Well, it's based on this idea of artificial neural networks. I'm not going to go into too much detail because it's a huge field. There's lots of literature already about it. But I'm going to describe how deep learning works on a conceptual level. So the main difference between those old 80s and the new models today is the advent of layers within a neural network. So they've added a stack of neural networks on top of each other. That wasn't possible in the past because of the training methods they use. So there's new training methods that allow these models to be used. And the way that they work is something like this. So the picture at the top is an example of some raw data that might go into your algorithm. In this case, it's a picture of a Formula 1 car. Great. It then begins to make greater and greater abstractions about that raw data. So the raw data, effectively, is a pixel. It's a pixel of information. And those pixels get fed into the network and gradually are built into higher and higher abstractions of that thing. So it would start off at the top as just the raw pixels, and then the next layer of neurons would maybe represent a small part of that picture. So it would train to form an abstraction about a bit of a tire, or a rim of a wheel, or an end plate on a wing, or a bracket for the wing, and so on and so on. Then there'd be another layer which takes those abstractions and builds it into another abstraction. This next abstraction becomes like a wheel, a wing, a rear spoiler, and so on. And then finally you can grab those together into a classification of a Formula 1 car. Now the difference is that if you give it another image, a picture of a normal car, for example, actually, if you lived in London, it might have a real spoiler. If you're not in London, it probably doesn't. But there are certainly some cars I've seen that do. Then that would actually, it would form similar abstractions, but once you get to that final layer, it doesn't fit that final abstraction of a Formula 1 car anymore. It'll become a new class. It'll be a class of type family car or normal car. So that's how the cascade of the deep neural network works. I'm not going to go into any more detail again because it's quite a very long-winded topic. Feel free to do your own research. It's very interesting. But now I'm going to show some of the things it can do, and this is kind of the exciting, the cool bit. I'm going to start with, I've got 4 examples. They increase in complexity. We start with a simple one and get more complex. This one is an example where you can go on the web and you can try this demo, and you type some text into the text box, and it generates some handwritten text. So this isn't pictures being pasted together. This is the neural network, the deep learning algorithm, generating written text. So it's kind of, usually it's done the other way. Usually people want to convert written text into normal text, but this is just a flip on that idea. So what does that show? Well, this is kind of the beginnings of a computer, of an algorithm, starting to look like a real human being. So if you just gave that text to a random person, said, who was that? A computer generated that? A person generated that? Let's say it was a person that wrote that. They wouldn't believe that it was a computer generating that. I'm going to focus on fraud a little bit because that's kind of what we're interested in at the moment. So giving a fraud example, you could, this is kind of an indication of what fraud systems will have to deal with in the future. A big problem at the moment for any finance institution is to try and originate the person. Origination is proving that the person you're talking to really, or dealing with, really is that person. Is it somebody that is pretending to be that person, or is it a computer? So if you just had a very simple system where somebody had to sign a signature, it could well easily be a computer. It doesn't necessarily have to be a person. You know, alternatively, this could be quite an interesting tool in terms of you could add to your origination software the ability to get someone to write some text and then verify that it really was them that wrote that text via the inverse of this algorithm. Example 2 is another popular one, so it's translation. So if you take some text, you can translate it into another language. And the way that they do that is they get a big bulk of text and they run algorithms and train this data to say what it should be. Over time it learns and then you can apply it to future problems. So again, this is kind of an extension of a machine looking like a human. It's a machine talking like a human. There's a great example on YouTube of a Microsoft guy in China who had done this, but he'd kind of taken it a few steps beyond. So he'd written a deep learning algorithm to convert his voice into text. He then converted the text into Chinese, and then converted Chinese into spoken Chinese. But the cool thing right at the end was that he actually used deep learning to train a model of his own voice to apply to the voice synthesis at the end of the chain. So he was speaking in his own language, but it was coming out of the speakers in Chinese in his own voice. So that's like, for Hitchhiker's fans, that's like a Babel fish. So we need to get that into a goldfish and then just like stick it in your ear or something. Next one, we've got sentiment analysis. On the front of it, this is quite a simple example, but there's some really interesting applications that could be applied to. So the idea here is to take a piece of text and assess the sentiment of that thing. So is it a negative thing? Is it a neutral thing? Is it a positive thing? So many people use this for movie reviews, stuff like that, for ratings. But this could be applied to everyday working life in most offices, you know. So most people are involved in writing text at some point, usually customer facing. You don't want that text to appear negative. You don't want to express negative things. You could run it through an algorithm and make sure that your words are positive things. Alternatively, you could take that a step further and just type in the context that you want to give and then let the algorithm actually write the text for you that makes it positive. In finance, there's a really cool one where you can apply this sort of technology to contracts. So you can analyze contracts to see what the contracts look like. Are there any issues with the contracts, loopholes with the contracts? Is there anything recursive? Things like that. There's all sorts of crazy stuff that could be done. And finally, we've got what's deemed like the most advanced and the holy grail, but computers being able to see, machine vision. It's a whole subject, and there's a bit of there's lots of fans of this, and people love doing this. I'm not sure why, because all of those other things are just as important. But here, on this example, we've got an engine where you submit a picture, an image, any picture. It could be off the internet, one you've taken a photo of, upload it to the net, and it will generate tags from that image, and then give you similar images which have already been classified. This is a bit more subtle because things like Google already do this, but the way that Google do it is that they look at the web page, they look at the text, they look at the name of the image, and then that's how they tag it. This is never seen any contextual information at all. It's just a picture. The machine learning algorithm has come in and isolated specific features and clustered them in such a way that they've applied tags to them. So the logical extension of this is actually the most publicized one is probably the driverless car. So you attach cameras to a car, allow it to drive itself. It's effectively just a classification task, but the world's so complex that people kind of gave up trying to manually write features and manually write algorithms in order to do the job. You have to turn to something that's a bit more adaptive like this. I had a friend in the US who worked for DARPA and he was a project manager for the DARPA Grand Challenge. It was in 2004 in the Mojave Desert, and he was in a chase car adjudicating one of the cars that was in the competition, and it was driving along and it was going nice and slowly. They didn't go very fast. This was like the first ever one that ever happened, and all of a sudden the car decided to put its foot down as fast as it could, swerve to the right, and it just hit a massive boulder and totaled itself. So he's just sat in the back and just had to hit this kill switch and just shut the entire thing down. So they went back and they had a look. And it had like a flight recorder in a box, and they had all the raw data there. They reran it through, and it turns out that this car, it thought it saw a pedestrian, so it swerved out of the way. It was just a cactus, just like that. So, you know, real life is far too difficult, I'm afraid. Okay, let's move on. So that's deep learning. It's a really, really bright, important future. You're going to be seeing more and more of it, but you'll be kind of seeing it behind the scenes. People won't be telling you about that. They'll be telling you about the new feature or the new product that they've got. But behind it, there's some really interesting stuff, and you can probably use it in your work as well. So this is a graph conference. I've not mentioned graphs once, so I better mention them now. One thing that we've been interested in recently is taking a graph problem and applying it to a machine learning problem. Because one of the fundamental drawbacks at the moment, and feel free to fix this problem because it's a real pain in the bum, is that the inputs to a lot of these algorithms are fixed. They have to be a known set of fixed things. And that's because you have a big set of data to train your algorithm, and then you apply that algorithm to new cases. But you need to massage the data in such a way that the new cases are the same as the training data, or else your algorithm won't work. So, how do you take a graph structure and put it into a machine learning problem? Because it's not a simple thing to do, principally because every little part of the graph looks completely different. If you have a graph that looks exactly the same every time, then it doesn't tell you anything. I'm going to refer a little bit to an example. This is a fraud demo, or fraudish demo that I stole off the internet, off Neo4j gists, and kind of edited it a little bit. Effectively, it's the traditional fraud case where you've got the idea of customers and they're linked via various things. So you can kind of see what you can do in order to try and build some sort of fraud detection system here. And you would write rules to detect certain patterns. So the key thing that, the new thing that Neo4j brings over traditional relational style fraud detection systems is that there's this concept of rings and groups and rings of information that's missed by the traditional tools and can be seen by Neo4j. But that's great. So what we'll do is write a simple query to find those rings or to find those linking information. However, that specifically relies on you knowing the fraudulent thing, the fraudulent path, before you deploy your application. So this is something that I would come up with, an engineer like yourselves would come up with, and therefore your fraud product is only as good as the engineer that wrote the pattern to detect the fraud. And how can you be confident? How can you be sure that A, you've chosen the right paths, maybe you're just wasting CPU cycles, B, that you've caught all of the fraudulent activity, and C, that you've got any hope of actually trying to beat the fraudsters in the future. So, like for example, even with that simple example, you've got the things like we're looking for the rings. I mean, like how big is the ring? Like what happens when it's not a 3-node ring, it's a 4-node ring? And oh, I forgot to write that. Or if it's a 5-node ring, what if it's a star or a different shape? Oh, I forgot to do that too. So what you could do is just use the traditional attribute values, use the relational data like you had. But it doesn't utilize the power of graphs. It doesn't utilize the connectedness between the data, and that's kind of where we want to be, because that's just as important as the numeric data. What about if we just take a graph and get a bit mathy, but you can represent an image of the graph in terms of a matrix of a a square of ones and zeros. And that matrix fully describes the picture of the graph. So it basically says, is that node next to that one? Well, 1 if it's a yes. So you can kind of describe that graph in a math way. But the issue with that is that, firstly, it doesn't encode any of the variables. You're throwing away all of the numerical information. And secondly, you have to choose a subgraph. And that subgraph has to be the same. You know what I mentioned earlier about the inputs to the machine learning has to be the same size. So that means your subgraph has to be the same size every time, which again is a bit pants. So the only thing that we have been able to do so far, this might probably a better way, but is perform some sort of transformation. And unfortunately, this kind of goes back a little bit to the days of old where we've got to generate features of the data that we had in the first place. However, it's not quite the same because we're not, well, in fact, yeah, I'm going to skip to the next thing. It's not quite the same because the idea is if we pick some features, it doesn't matter what they are, just generate loads of them. Anything you can think of, from simple things like the number of neighbors to the number of edges, the total number of nodes, total number of edges. The chap in the, I've forgotten your name, sorry. The guy, forget it. He talked about loads of algorithms that you can perform on graphs. You could provide all of them, and they will then become the inputs to your neural network. So you've got lots of different metrics that are just describing that graph in some qualitative but holistic way. Yeah, and then we've got some more here. Yeah, okay, I think you get the idea. So, so we put all those in, but then we use the deep network, the deep learning algorithm, to tell us which of those features are important and not important. So we're not actually adding any bias in there. We're saying, out of every feature we could possibly think of, you choose. We're taking the decision out of our hands. You choose which are the best ones, and that's purely based upon the data. So, an example. So I've spoken to a few guys today, and the biggest problem I have in the financial world is that all of them just won't give you any data. They would rather kiss your mother and slap you in the face than give you any data of any kind. So I went for a completely different field, and this is a great example. So this is a chemistry example, and the trial was to, given a set of molecules, compounds, what effect would that have on rats? So they gave these compounds to rats, and basically, did they die or did they not die? So it's a bit gruesome, but it's quite interesting. And the beautiful thing behind it is that there's no numerical information in there at all. It's purely described by a structure of the atom. So it's a great graph problem. So we did all of those things. We took loads of features, all the ones we could think of. We then put it into a deep learning algorithm and let the algorithm choose which of the features, and then had a training set and a validation set and all of that goodness, and try and predict, basically, what was the outcome of a new compound that it had never seen before. I used Python in this, so yeah, I've probably won't have time to show any slides at the end, but there's loads of tools out there. Basically, your language of choice will have some sort of machine learning tools. I really like Python, but R, MATLAB, Java, Scala, anything you can think of has already got really good things. Oh, and you could use Neo4j as well. There we go. But have that in there as well. There we go. So the results were 28% average error. The best ever that anyone's ever got is 17. Now, it's okay. The competitor in me wants to really get better than that. But I spent about half a day on this. And this is something that trained chemists would spend years learning about compounds and how they react in the body and the different animals and whatever. And me, within half a day with a computer, was able to get some really good predictive results. So just as an example, these are two new molecules that has never been seen by the algorithm, and it's given you some probabilities of whether it was dangerous or not dangerous. There's evidence of it being dangerous and not being dangerous. And we've got the first one here, diclothes, or I can't even pronounce that. So I mean, this is just it's a great example of it's taking away the specific knowledge you need in order to perform a task. So if we bring it back to fraud again, so fraud, people, companies, finance institutions that are interested in financial crime have to employ really smart people to analyze the data and have a look at every fraud case that they can. I could come along, or a customer service agent could come along and perform this analysis and generate the same results in a very reasonable and performant way. So, on to a bit of software. So the way that we see this happening is it's effectively you have two processes. You have offline processes and online processes. The online process is the thing that attempts to detect the fraudulent activity in real time. So maybe you get a new transaction in, you run some analysis to see if that was fraudulent or not. But the key thing here is the data. I was speaking to someone about data earlier on, and the most important thing is we get access to that raw data, because it's the raw data that contains the information. All of the examples you can probably find on the internet, and generally even like for Neo4j examples, they're all very simple, high-level problems. And to do this properly, you need the raw data. So we're talking like, phone calls, phone records, customer service records, applications, documents, transactions, all of these things. Any one of those things you don't know, you're letting the machine decide. Any one of those things could be really important to detecting the thing you want to detect. And then you have the offline task, where you perform the offline training, which can often take quite a long time, depending on the complexity of your model. There's also some human interaction in there as well, where an expert would come in and say, okay, you've got an example of fraud here, I know that was fraud, but looking at this visualization, there's a cluster of other incidents as well, but they're not flagged as fraud. Why not? Let's go and investigate. They do their investigation, they find out it was fraud, they add that flag in and then retrain the data. So it's a continuous process of improvement. So from the offline point of view, the whole point of it is to generate these patterns, for a better word, for the live database to use. This could be anything from a pattern that's encoded within the deep learning network itself, or it could be a pattern that goes back to a graph. Maybe it is that simple cyclic pattern. But the whole point is that you need to take your data and you need to provide a transformation if you've got to use it with graphs. And then you've got the online part of it, which is a bit similar, but the focus here is on the real-time online validation or classification of whether it's fraudulent or not. And that essentially goes to a fast database, or it goes to a fast algorithm, and you get results in real time. A little bit about architecture. So yeah, Trifork's a business which aims to use the best tool for the job. So we're not only using Neo4j, there are other technologies out there that can help you to do this job. But they all kind of fit into this paradigm. You've got data coming in, you stuff it into a database of some sort, we call it a staging database. You extract what you need to perform the offline analysis and the research, and then you forward the important bits of information you need to do the online stuff. And the purpose of doing that is that basically the less data you've got, the easier it is for the algorithms to do its job. So you only want to forward the data that's really important. So in any of these cases, you should usually have a human in the loop somewhere to basically continue improving these processes and improving these performance measures. And at the output, you've got all the things that feed back into the traditional system. And I think I'm about bang on time, so I think I'll stop there. Okay, thank you very much. Cheers.